Dr. Guha, I think we can start now.
2 minutes from now.
Okay, okay, okay.
Has Anita ji joined?
Yes, yes.
Okay, okay.
You already joined.
Is our TIC here? Hello?
Yes, I am in time, sir. I am in time.
Okay, okay. Thank
Okay,
you, thank you.
okay.
Thank you very much. I think Anita ji can start now.
Okay, thank you. So we are starting. Good afternoon, esteemed participants. Welcome to this one-day international webinar, Bose-Einstein Condensation, BEC, a journey into the quantum world, organized by the Department of Physics, Santipur College, in collaborative with IQAC, Santipur College. It is a glorious moment to extend my warm wishes on behalf of the Physics Department, Santipur College, to convey my heartiest gratitude to our today's speakers, Dr. Moumita Indro and Dr. Orpita Das, all participants from various parts of the country, Dr. Brojo Kishore Goswami, President Governing Body, Santipur College, Dr. Subroto Rai, Teacher in Charge, Santipur College, all teachers of Santipur College, and all non-teaching and students of our college. Now, Bose-Einstein condensation BEC, a fascinating state of matter predicted by Albert Einstein and Satyendranath Bose in the year 1924. Last year was centenary of this phenomena, and this state is achieved by cooling a gas to incredibly low temperature, close to absolute zero, by Eric Cornell and Carl Wyman, University of Colorado Boulder, using rubidium atoms in 1995. BEC is a state of matter where a macroscopic number of bosons occupy the lowest energy state. And this very low temperature, close to absolute zero, how close? That is 10 to the power 9 Kelvin, known as NK or nano Kelvin. BEC are not just theoretical curiosities, thus have significant implication for various fields, including quantum computing and other quantum technologies, ultra-precision measurement of time, length, and other physical quantities, etc. Today's discussion will take all of us through the intricacies of BECs, explaining their properties, creation, and application. We have two young, very promising women speakers, Dr. Moumita Indro, postdoctoral fellow, Department of Physics, IIT Guwahati, India. Actually, she is a very jewel former student of our department. We all are proud of her. And second speaker, Dr. Orpita Das, Royal Society Newton International Fellow, Department of Physics, Durham University, UK. Our first talk of Dr. Moumita Indro, her topic is a brief introduction to interacting many-body system from BC to FQHE. It is a talk on the theoretical foundation of BEC and its connection to other quantum phenomena. And topic of the second speaker, Dr. Orpita Das, is taming the cold, creating and exploring ultra-cold molecules in the quantum lab. It is a discussion on the experimental techniques used to create and manipulate BCs. We hope that today's discussion will spark new ideas and delve into the heart of the quantum world. Once more, we would like to express our sincere gratitude to our distinguished speakers and enthusiastic participants. Let us begin this exciting journey into the quantum world of BEC. Here, I am sharing one announcement. The feedback form will be shared during the session. Please submit it to receive the certificate of participation. And I am requesting all participants, please keep your microphone on mute. Thank you.
Okay, next it is my turn to introduce. I, Dr. Jyotirmoy Guho, Head Department of Physics, Santipur College, warmly welcome you all in this international webinar organized by the Department of Physics in collaboration with IQAC of Santipur College. Established in 1948 and NAC accredited, Santipur College carries forward a rich tradition of cultural heritage and academic excellence. Inspired by this glorious legacy, we have chosen to celebrate 100 years of the wonders of quantum advancements. Though the centenary officially concluded in 2024, it is never too late to acknowledge a century of groundbreaking scientific achievements that still play a defining role in shaping our world. In 1924, the brilliant mind of Professor S.N. Bose sent a paper on quantum statistics of photons to Einstein, who extended the idea to atoms and suggested that near absolute zero, bosons would collapse to a single quantum state, thereby predicting a new quantum state of matter called the Bose-Einstein condensate that was experimentally realized by Cornell, Wyman, and Ketterle in 1995 using alkali atoms that won them 2001 Nobel Prize. NASA launched the Cold Atom Lab in the International Space Station in 2017. In this webinar, the first speaker, Dr. Moumita Indro, joining us from IIT Guwahati, will lead us to interacting many-body systems ranging from Bose-Einstein condensation to fractional quantum Hall effect. Our second speaker, Dr. Orpita Das, joining us from Durham University, UK, will focus on techniques and tricks employed to slow down atoms and molecules in an ultra-cold environment to create Bose-Einstein condensate. The main session with our speakers will begin shortly, and Dr. Dipankar Bhattacharya, Associate Professor in Physics, will conduct the question-answer session. Before the main session begins, I invite our Honorable Teacher in Charge and Secretary Governing Body, Santipur College, who is also the chairman of this webinar, Dr. Subroto Roy, to address the webinar, sharing his thoughts and ideas in a nutshell. So over to Dr. Roy, our teacher in charge.
Okay, thank you. A very good afternoon to all. I, on behalf of Santipur College, welcome most cordially the distinguished research person and all the participants of the webinar. This is a laudable effort on the part of the Department of Physics I appreciate the sincere involvement and proficient engagement of the head of the department, Dr. Jyotirmoy Guho, the conveners of the webinar, Dr. Anita Gangopadhyay and Mr. Subhai Choudhury, coordinator of IQAC, Dr. Dipankar Bhattacharya, and the faculties of the department. I hope the lectures on the title, Bose-Einstein Condensation, a journey into the quantum world, being delivered by the speakers and discussion followed by the presentation will highly benefit the students and other participants attending the webinar. I heartily wish the webinar a remarkable success. Because of my emergency assignment, I have to leave early, and I would request the HOD of Physics and coordinator of IQAC to take care of the formalities and other related things and issues. Thank you all once again.
Thank you, Dr. Subroto Roy, teacher in charge, Santipur College, for your enriching observations and thoughtful inputs. I now have the pleasure to introduce the first speaker, Dr. Moumita Indro, a student of Santipur College way back in the period 2012 to 2014. She did her bachelor degree in 2014 as well as master's in 2016 from the University of Kalyani and PhD in 2022 from the Indian Institute of Engineering, Science and Technology, Shibpur. She enjoyed DST fellowship and her research area was quantum Hall effect, strongly correlated system. She was a postdoctoral fellow of Electrical Engineering Department, IIT Bombay, in the period 2022 to 2024, working on quantum dot-based semiconductor devices. From 2024 onwards, she is working on quantum droplets and dipolar BEC in IIT Guwahati. We now look forward to hearing from Dr. Moumita Indro as she presents her talk. Please keep your microphones muted to prevent background noise. The question answer session will begin 45 minutes from now, during which you may unmute to ask questions. Now over to Dr. Moumita Indro for her talk.
Thank you, sir, for this nice introduction. So I'm sharing my screen first. Is it visible?
Yes, visible,
Yeah.
visible.
Hi, I am Moumita Indro, and it's truly an honor and also a deeply emotional moment for me to be here today, and not as a speaker, but as a former student of this eminent institution, Santipur College. And I want to convey my heartfelt thanks to all my respected teachers and honorable TIC and all the conveners, and for giving me the opportunity to present my work and share my thoughts to the next generation students. So currently I am working in IIT Guwahati as a postdoctoral fellow, and mainly my research area is in interacting many-body quantum systems. So today I want to give you a glimpse of this fascinating world of this interacting many-body quantum particles. So mainly I'll go from Bose-Einstein condensation to fractional quantum Hall effect, which is strongly interacting system. So this is the title of my talk. So here is a brief overview of this talk. Like firstly, I will introduce many-body system, and then how this interaction leading to exotic phases of matter. Then I'll just give a brief discussion over bosons versus fermions, and then I'll introduce Bose-Einstein condensation and its property and some research directions. And then I'll go to the quantum phase transitions like BC to BCS crossover and superfluid to Moss insulator type of transitions. Then I will discuss fractional quantum Hall effect, and I'll show some research directions, and finally I will show some proposal of fractional quantum Hall state on rotating Bose system. So, so I'm first going to this many body system. What is this? What do you mean by many body system? From the name, we can say like there should be some large number of particles. That is more than one particles will be there. And if there are more than one particles, what is happening? Something happens, they will interact with each other. Like as per our common example, we can say if in a classroom just one or two students is there, then what happens? There will be some quiet place. But if a classroom, just you assume a classroom full of students, then there will be some noise or some chaos will be created because they will talk with each other, or they are interacting with each other. So that's same for quantum particles also. They will interact with each other, and the behavior of the whole system, it cannot be understood by simply adding up the behavior of the individual particles. So there is a nice paper by P.W. Anderson. The title of the paper is More is Different. So really, when more number of particles is there, the scenario becomes different, and it's really interesting. So these many body systems are important because our real world materials, these are consist of many particle systems, and they exhibit some rich physics like some quantum phases, superfluidity, superconductivity, and topological phases. I'll discuss some of the phases in my talk. And we can understand these exotic phases by bridging quantum mechanics, statistical physics, also field theory. So it's really important. And there are some examples of these many body system. We can think of when electrons are in a solid body, then they interact with each other by Coulomb interaction. Also, when ultra cold atoms are there in optical lattices, they are also interacting with each other by contact interaction or dipolar interaction. Also, another example, we can say fractional quantum Hall systems. I'll discuss it in details in the latter part of my talk. So basically in fractional quantum Hall system, there is the presence of magnetic field, and the particles are interacting with each other with repulsive Coulomb interaction. So now I'm going to the three basic or conventional phases of matter you all know, that is solid, liquid, gas. So what is the main difference between solid, liquid, and gas system? From the figure, anyone can say that there is the interparticular separation distance is higher in gas than the liquid and solid material. So it's one difference. And another most interesting difference is that in solid materials, the particle-particle to interaction is most, or it is highest interaction is there than the liquid and gas. So here solid material is strongly interacting and liquid is not that much, it is weakly interacting, and this gaseous system is sometimes not interacting. So this is the main difference. And also in solid materials, we all know in our basic solid state course, like solid materials can be some crystalline nature, or also they can be some amorphous nature. So if we apply Bloch's theory or chronic Penny model, that is in our postgraduate course, it is there, then we can show there is some formation of buoyants in the solid material. Like there is the formation of conduction band and valence band. And with this idea, we can distinguish the different solid materials into insulator, semiconductor, and conductor. Conducting material, they are these two bands, conduction and valence bands, are overlapping, so there is no band gap, and they conduct electricity. And in case of insulator, there is band gap is higher than 3 electron volts, so it cannot conduct electricity. But semiconductor is most interesting. Their band gap is less than 3 electron volt, and there are so many semiconductors here. We can tune this band gap. So in modern days technology, these semiconductors are highly used, and we can just tune its band gap, and we can tune also its electrical and optical properties for our different purpose. So that's the broad sense. So if we go some quantum design, like with effect of interaction, there are some exotic phases of matter are like generated that go beyond the conventional solid, liquid, and gaseous state. And if observed in some ultra cold systems or some quantum materials where particles are correlated to each other. So I'm just noted some of the phases. So firstly, a superfluid is it's a phase of matter where the fluids flow without any friction. There is no viscosity. And another is superconductor, same type. Here current conducts without any resistance. So here also the electrical resistance drops to zero, and magnetic fields are repelled by this superconductor. And another interesting is not insulated. It's defying the band theory predictions, but it's an insulating state caused by some strong electron repulsion. And another topological insulator. Topological insulator is an insulator phase in bulk, but it has some conducting edge state or surface state that are highly conductive. And it's also protected by topology. And another semi-metal is also important nowadays. It is also using there is also overlapping bands like conductor, but there is a low carrier density. That's why it is known as semi-metal, and its example is like graphene. So now I am coming to quantum particles and their distribution function. So we all heard of Fermi-Dirac distribution, Bose-Einstein distribution, also Maxwell-Boltzmann distribution function. So general form of the distribution function for quantum particles is follows like this. Here epsilon is the energy, and mu is the chemical potential, K is Boltzmann constant, T is the absolute temperature. So in case of Fermi-Dirac distribution, that is some fermions obey this type of distribution. This plus sign is coming. So here, basically, we know fermions means which have half integer speed, like half, 1/3, half, 3/2, 5/2, like that. So they are known as fermions, and they obey Pauli exclusion principle, and they have maximum occupancy 1 per side. And Bose-Einstein condensation, it is obeyed by bosons, and it has negative sign here in the denominator. And it applies to both particles, mainly in photons and helium-4, which have integer speed. And here, multiple occupancy in a single state is found, and it leads to Bose-Einstein condensation. That I'm coming in my later slide. So both these two quantum distribution, Fermi-Dirac and Bose-Einstein distribution, these goes to classical limit at high temperature and low density. So it behaves like this type of distribution function known as Maxwell-Boltzmann, that classical particles follow this type of distribution. So there is a here is a comparison between this Fermi-Dirac, Bose-Einstein, and Maxwell-Boltzmann. So that's the basic things. So I'm coming to the new state of matter that is known as Bose-Einstein condensate. Basically, this Bose-Einstein condensate is known as fifth state of matter. Solid, liquid, gas. After solid, liquid, gas, there is another state is chem. It is known as that is plasma. It is known as fourth state of matter that is found in environment of stars and galaxies. That is high energy state basically. And after in 1924, Satyendranath Bose first introduced his work, and the Albert Einstein basically carried forward this work, and he come to a natural conclusion that at some low energy on low ultra low temperature, these both particles condense into a single quantum state, and they form a new state of matter known as Bose-Einstein condensate, named after these two scientists, Satyendranath Bose and Albert Einstein. So for Bose-Einstein condensation, you may follow this book. This is a very good book by Petri. And yeah, so I'm coming to how this condensation forms. There, it is just a snapshot from an YouTube video. So just consider when particles energy is higher, like temperature is high. So these Bose atoms that behave like a free gas or they move like freely. But when temperature is lowered, like this figure, when temperature is lowered, they are coming to low energy states and they behave like some quantum particles and they shows like some matter waves. And these matter waves, when the temperature is further decreased, these matter waves increase in size and they overlap with each other. So basically, after some below some a transition temperature Tc, these all the particles, all these Bose atoms, they condense into the lowest energy state, that is its lowest quantum state, and all the particles wave, these behave like a collective wave, or this is known as collective phenomena, and this is known as condensation of these Bose atoms. So it is first experimentally achieved by these scientists, Wyman, Cornell, and Ketterle, and they first cooled a rubidium atoms in 170 nanokelvin in 1995, and these three scientists also received Nobel Prize in Physics in 2001. Basically, Bose-Einstein condensation is introduced in 1924, but at that time, there was no experimental advances or no, also laser was not invented at that time. That's why it is discovered many years later, physically. In 1995, first it was achieved in experiment. So I'm coming to this transition temperature. Just I mentioned in my earlier slide that after below some transition temperature, this is sometimes known as critical temperature, this Bose-Einstein condensation is occurred. And we can say this number of excited particles at temperature T below the critical temperature can be related by this formula. Here Tc is the transition temperature, T is the temperature of the gas, and N is the total number. And also the number of particles at the ground state, that is the atoms at the condensate state, it can be found as N0, that is total number minus N of excited state, that is giving by this. So we can find out the fraction of particles which are in BC state, and it is a plot here. We found that when T is below Tc, then this N0 by N, it goes to 1, like N0 is nearly equal to 1. And this number of particles in excited state, it is falling, it is going decreased. So basically, BC exactly looks like these types of nature. Here, this is the velocity distribution plot. And here it is the first found by Gila group in University of Colorado. And it is for the rubidium atom condensate. So we found that there is a drop of condensate at the center, and the condensate is surrounded by the uncondensed gas atoms. So basically, to occur this BC, some systems should be ultra dilute. Typical density is like 10 to the power 13 to 10 to the power 15 per centimeter cube. Whereas the typical gas density is more than this. So this is the basic criteria for the BC. So I am going to what happened when BC in presence of interaction. So we know the effective interaction between two particles or two Bose atoms at low energy is given by some constant value in momentum representation. This constant here consists of AS. AS is the S wave scattering length, and H cut is the reduced Planck's constant, that's just h by 2 pi, and N is the mass of the bosons. So we can represent this interaction between the two Bose atoms in coordinate space like this formula. Just U0 is multiplied by delta function. So we all know delta function is behaves like this. At some point it has value and other point it is 0. So when two particles will come to in contact, they will interact with each other, and otherwise it will not contact. So that's why it is called contact interaction. So basically both atoms are interact via each other by contact interaction, delta type of potential. And we can write down the system's Hamiltonian for in atoms in ultra cold dilute Bose gas like this. So here H is the Hamiltonian, that's is related to the total energy of the system, and it is just sum over all the particles, individual particles, kinetic energy plus potential energy, and also there is the particle to particle interaction term. So this Hamiltonian is the total Hamiltonian. Also, we can write down the many-body wave function for the system that is given by this. Here, psi is the total wave function of the system that consists of all the n particles. So it is a function of all the particles coordinate, and it can be written as a product of the single individual particles wave function. So all the single particles wave function is normalized to unity, which follows the basic quantum mechanics. And basically this product of this individual wave function, this is known as mean field approach. So also we can write down the energy of the system in terms of this Hamiltonian. So this is basically coming from here, and it also we can represent in terms of the total many-body wave function. So this is a energy functional function of psi. So we can find out the system's equation by differentiating this energy functional. So if we just differentiate this energy functional, we just obtain the system's equation that is known as Gauss-Petersky equation for Bose-Einstein condensate. And basically, this is a Schrodinger-like equation. So here, this H star del psi del T, this is the energy operator types. Like we know that Schrodinger equation is H psi equal to E psi. So this is the E psi types of part, and this is the H psi type. But here, just one difference is that this H contains some nonlinear term, that is some psi square quadratic term. So that's why it is sometimes called as a nonlinear Schrodinger equation. So here this psi r comma t, this is basically condensate wave function, and its position and time function. So in theory, it is not exactly solvable in this equation. This is nonlinear differential equation, so it is difficult to solve exactly. That's why people use some numerical methods to solve it numerically. And the process is, firstly, we use some Gaussian type trial wave function for this psi, and then if a time evaluation of this wave function is done, and then we can observe some wave function, or this is the basically 2D surface plot of the density, that is psi squared is plot in the z-axis, and x and y position is varied in this. This is the solution for 2D Gauss-Petersky equation. And in this paper, they just showed the numerical procedure and how this this time evaluation is done. So basically, to solve this differential equation, some Fourier Tank-Nicholson method sometimes use, or sometimes people use some Fourier time split spectral method that also nowadays is usually used. So this for this there are some codes you have to write down in Fortran or Python, basic codes. Then you can solve this type of equation according to the system configuration. So now I'm coming to rotating Bose-Einstein condensate. So what is that? Like, just assume like there is a, like Bose atoms are confined in the XY plane. That is, it is a harmonic potential is there is harmonic trapping potential is there, and all the atoms are trapped in the XY plane, and the whole system, this whole system is rotating about Z axis. It is trapped in XY plane, and rotation is perpendicular axis. So, and the rotation frequency is very high. So we can also write down the Gauss-Petersky equation for this type of system. That is same. Here, this V external potential is given by this just a harmonic type potential, like half m omega square x square plus y square, 2D potential. Okay, and there is some interaction part is there. It contains psi square term, and here U0 is the interaction, and n is the total number of particles, and this minus omega Lz, this is the rotational energy term. that is coming due to the rotation of the system. So it is also nonlinear Schrodinger equation. And if we solve this type of equation, we get this is the solution of this rotating DC. Some vortex types of lattice is formed here. Vortex means some deep position is observed, and it has a particular pattern also found sometimes. So also it is observed that when rotation rate is increased, the number of vortices is increased rapidly. Like here, the 2D surface plots are shown. That is, psi square is plotted as a function of xy. And here this omega value, that is rotational frequency value, is changing. It is increasing by from 0.35 to 0.90 with increment of 0.05. So it is observed that this number of vortices is increased rapidly. And some pattern formation also is found. So this is very interesting really. And also figures are very beautiful. So I just put it here a quotation by Barton Russell. He said that when mathematics are rightly viewed, it possesses not only truth but supreme beauty. Really, when sometimes we feel like boring mathematical equation, but sometimes its solution gives some fascinating, some interesting result. So it's the inspiring one. Now I am going to transition to lattice model. So firstly, what is going to optical lattice? What is optical lattice? Optical lattice, you can say it is like an artificially made lattice structure or periodic potential created by interfering laser beams. So to counter propagating laser beams when but it is just prepared by to counter propagating laser beams. It may be found in 3D of course. If we have to need like 6 laser beams from each the direction, and then we can make a lattice structure in 3D also. So basically, we are creating some potential like that, which has sinusoidal nature. And here, this basically optical lattice looks like some curtain of the eggs, where eggs are kept in a curtain. It looks like exactly like that. Some peaks are there and some tough position, like some dips are also there. So atom may stay in the maximum position, also some in the minimum position, according to our laser detuning and all. So basically, by laser beams, we just making some standing waves, and it is creating some interference maxima and minima. And these atoms experience a force due to the electric dipole interaction with the light. That is, light matter interaction is happening, and these atoms got trapped in that position. So that's the procedure, and I think the next speaker, Dr. Orpita, can tell about in details for these experimental techniques and what is actually done in lab. So yeah, it will be clear later. And why it is important. So basically, it can mimic the periodic structure of solids, and but it has highly tunable environment. We can just tune the lattice depth, that is this V0 value. This is can be tuned by the intensity of the laser light, and also this by changing the wavelength of laser light, we can change the lattice spacing. That is the distance between these two maxima or distance between two minima can be also tuned. And also by polarization and detuning, it also can determine trapping configuration. That is where actually the particle will get trapped. And also this atom light interaction scale can be tuned also. So basically for a theoretician, this type of model actually enables us for the simulation purpose, and with the tight binding models like one is like Bose-Hubbard model. So in this Bose-Hubbard model, it is basically a lattice model describing Bose atoms are trapped in optical lattice, and it has a Hamiltonian consists of a kinetic energy part that is contains the hopping term, and another is interaction energy that is contains the potential energy type form. So we can think of a lattice this type. So here basically this T defines the probability, tunneling probability or hopping probability, like how much the chance or probability is there to hop a particle from ith position to jth position or whatever, that is just next near neighbor position. And this U basically defines the on-site interaction strain. And here this A dagger and AJ, this is basically using second quantization in quantum mechanics. So in second quantization, we are just dealing with that wave function as like some field, and we think about some ladder operator, some known as creation operator and annihilation operator. Basically here AI dagger, this is the boson creation operator. We can think that AI dagger, it's just creates a particle on the ith side, and AI, this is the annihilation operator. You can think AI is the just destroys or annihilate a particle from the ith side and all. So in this type of model, we can just solve these Hamiltonian by some exact diagonalization method, or some techniques are there. So we can find out systems energy and also phase diagram and all by tuning these T and U value. So basically here the lattice depth has a role. If we take a shallow lattice, right, like V0 value is lower, then what happens? There, if V0 lattice depth is low, then particle can easily hop to one position to another position. So there is a, we can say that hopping amplitude is will be large. And in case of deep lattice, so the opposite phenomena, where hopping probability will become less, and particle will be just trapped in a single site, and it will be we get localized type of wave function. So basically from here we can get a phase transition from two phases, superfluid phase to Mott insulator phase, when channeling or hopping probability is much greater than this on-site potential U, then particle can easily hop to one position to another position, and atoms get delocalized, and this system behaves like superfluid, like without any friction, then can move to one position to another position. And in case of Morse insulator, when U values is much greater than T, atoms get localized in a fixed position, and there will be a fixed number of particles per side, and it will behave like an insulator type of phase. So basically it's a quantum phase transition from superfluid to Morse insulator phase. And for this superfluid phase, as I told, there will be atoms get delocalized, they can move to any other position, and there exhibits a long range phase coherence. Due to this phase coherence, we get some interference or absorption minima. It shows some peaks value, and if some maxima and minima positions was observed. And in case of Mott insulator, where interaction strength is much greater than the hopping parameter, then atoms get localized to some a fixed position, and there are fixed number of atoms per site and no phase coherence. That's why we did not get any peak position, and there is no interference pattern. A continuous distribution of particles which we will found. So this phase transition basically experimentally realized by first Glainer, and this picture I collected from their Nature paper. It is just showing some absorption images of multiple matter wave interference pattern. Here basically V0, that is lattice depth values, are varying. Lattice depth value are increasing from A to H. So there is a prominent observation of is found from superfluid phase to Morse insulator type of phase. This is not a sharp phase transition. It's like a continuous evaluation from superfluid phase to not insulated phase. Okay. Hmm. Next, another phase transition I'm going to tell, that is BC to BCS process. So basically, BC system can be found for fermionic molecules also. Like if two fermions are make some molecules, like lithium can make lithium is as a fermion. If it can maybe form like some molecules, then these molecules also can show these Bose-Einstein condensate types of phenomena. So we can say these are two fermions. They are interact with each other strongly and they form a molecule. And these molecules can show Bose-Einstein condensate and they just condense into a just lowest quantum state. So this can be is known as BC of these fermionic molecules. And if just we can if we tune the interaction strength between these two fermions, like if interaction is reduced, like from then we found some crossover is observed from BC to BCS type of nature. So first I have to tell about what is super pair. Some of you, I think you heard of this Cooper pair, because Cooper pair is introduced by Barden, Cooper, and Schiffer, three scientists. They explain the superconductivity phenomena by introducing this pair. They just assume that two electrons, like having opposite spin and opposite momenta, they just coupled with each other by with interaction or by due to lattice vibration or phonon coupling also it is called. So by phonon coupling, they are like made a combined particle, and they just make some move in a coherent way in superconductor. That's why there is no resistance is found in case of superconductor. So if we just tune the interaction of these molecules, like then it may go to from strongly bound molecules to weakly bound Cooper pair type of state. So that is type of phase is known as BCS or BCS transition from BC. So that this tuning of this interaction is done by basically applying some external magnetic field, and this is known as phase-back resonance. And it is first experimentally achieved in ultra-cold fermionic gases like in lithium, potassium. This type of phase transition is found. And there is an experimental paper also in 2014. They shows the qualitative phase diagram from BEC to BCS crossover. So this is also a continuous evaluation, not a sharp phase transition. Now I'm just telling about some recent advantage in dipolar BEC. Dipolar BEC means it just contains some dipolar atoms or molecules which have a strong magnetic dipole moments, and here there exhibits some long range interaction, that is dipole-dipole interaction in addition with contact interaction. So basically they are interacting with long range dipole-dipole interaction and they have strongly dipole moment. So firstly, there is a recent observation in that dysprosium and iridium atom. These are having strong dipole moment, and some quantum droplets type state is observed in these two atoms. Basically, quantum droplets is a mixture of two different dipolar species. You can say two species, mixture of two dipolar species is there. Then they can form like a liquid droplet type of form, and it is a self-bound state. Basically, these intraparticle interaction, that is between two species, different species, they have some attractive interaction with each other, and they just want to collapse these droplets. But this interspecies attraction, that is basically coming from quantum fluctuation, that is repulsive in nature, and that tries to make the system unstable. So basically, this is a self-stable state, and it is also bound state. So it can be explained beyond main field theory. Some Li Huang Yang LHY interaction term we have to introduce to explain these types of BEC mixture. And this is basically firstly found in 2016, so it's a recent topic. And there are so many works are going on these quantum droplets or dipolar BC system. So basically, some super solid type of phase transition is found. Some in these quantum droplets, some periodic density structure is observed, and in this dipolar system. And also, when this dipolar condensate is rotated, some vortex formation, also some periodic lattice type of structure is found. That includes a phase diagram between type, checkerboard type, crystalline phases. So that's are all recent works. So you may follow by searching quantum droplets. You will get some idea about it. So we have observed that Bose-Einstein condensate, it's a like an diverse, it is involved with some diverse field of research, and it's a like a fusion of the scientific tradition of the all fields like atomic physics, statistics, optics, and these are all connected with this BC. So it's really fascinating and interesting also. So I'll take a pause for 1 minute for going the next question. If you have any question, you may ask me.
Orpita, I have a naive question about vortices in the BEC. So the vortices observed in the BEC, it has the topological charge like the normal optical vortices, like Lagrange-Gaussian beams,
No,
LG1.
it's not. No, it's not a political quantity. It's like
No,
some. Sorry.
so there is no topological charge in case
No,
of,
no topological sense.
okay.
Some pattern formation like found. It is due to the interaction between the particles.
But you need to rotate the BEC, no?
Yeah, for in rotating BC, all this vortex type of formation is found.
So Orpita, there is, sorry, in Momita, there is a question from, can you see the question? Can quantum droplet
No.
use as qubits? This is a question from Sneha Sharma.
What qubits?
So can quantum droplet use as qubit? This is first question, and second question is from Sumon Das. What is quantum droplet? You already explained what is quantum droplet.
Yeah, quantum droplet is a, you just can say it is a self-bound state of mixture of two BEC. It may be dipolar BEC or any just two normal BEC mixture can be called as quantum droplets.
So can the
And,
use as a
sorry?
qubit? This can be used as a qubit.
For that question, I also don't have any idea about it. I'll think about it. I think for qubit it is not used. I have not explored that. I have to just revisit this. I don't know.
So there is another question from Chanchal Bharadwaj. Can
Yeah.
semi-metal be used in chips like semiconductors? Very deep.
Yeah, it can be used according to our like priority or what the requirement is needed. According to that, these types of phases are used basically in modern technologies. So
Okay.
it depends on our requirement.
So there is another question. So I think this is the last question.
Yeah.
After that, she will continue. So which experimental method physicists use to change the particle to BEC? So there, I think our next speaker, Orpita, will.
Yeah. It will be clear after that talk. Yeah.
So there, she will discuss about it. Okay.
Yes.
So let's continue.
Okay, I'm just continue. So I'm going to my next part, that is strongly correlated electron system, that is fractional quantum Hall effect. So firstly, that's the basic thing about Hall effect experiment in our graduation or post-graduation courses. It is there, I think. In laboratory classes, some experiment is there. to determine the magnetic field strength or to calculate the resistance of the Hall resistance and all. So basically, this is a classical phenomena, and it is firstly observed by Edwin Hall in 1879. So if we place any conductor or semiconductor in a magnetic field, then just we can find that some charge charge are accumulated in the transverse side, and a voltage difference is found in the transverse direction. That is known as Hall voltage, and this Hall voltage is by divided by current is known as Hall resistance. So it is found this Hall resistance takes it is linearly varied with magnetic field. Here B is the magnetic field, rho is the density of electron, E is the electronic charge, and C is the speed of light. So we can just find that the Hall resistance is linearly proportional with magnetic field, and another resistance that is known as longitudinal resistance, that's just Vx divided by I. It remains constant throughout. That follows the Drude-Lorentz theory. That's why this is constant. And if we perform the same experiment, this Hall effect experiment in a 2D sample, like in place of this bulk material, we have to take a 2D electron system, being graphene or any 2D MOSFET, anything 2D electron system, that is the main criteria. So also same, we have to apply magnetic field in the perpendicular direction of this 2D system. Then we find that this curve just takes some this type of nature. Like here, Hall resistance, that is Ra, it takes some quantized value. Like it takes like value h by mu squared. Here h is the Planck's constant, E is electronic charge, and mu is some number. So this upper curve, this is basically Hall resistance, and it is found that at the position of the plateaus, that longitudinal resistivity that becomes zero or takes some minima value, and from the position of this minima value, we can find out the values of this mu. So it is found this mu sometimes takes some integer number like 2, 3, 4. This reason is known as integer quantum Hall effect. And when magnetic field strength is high enough, like greater than 10 Tesla, then mu takes some fractional values. And this design is known as fractional quantum Hall effect. So basically, it is a strongly correlated electron system. Their particle to particle interaction is very strong. And these new values are found like 1/3, 2/5, and so on. So till now, 80 above fractions are observed in experiment. This is basically an experimental curve, and it is first introduced by Krisling and Stromer Gossard, and they found this type of observed result. So to explain this type of like these fractional quantum states, there are some theories. So what is happening in this system? We can say that in presence of magnetic field, this 2D density of state of the particles that condense into some discretized, quantized energy levels, and this is due to the quantum phenomena. And we can say these energy levels are separated by cyclotron energy h cut omega c, and these levels are known as Landau levels. And these Landau levels are highly degenerate. It can occupy more than one number of electrons. And we can find out the degeneracy of these Landau levels by V by phi 0. Here phi 0 basically flux quanta. Uh, According to quantum mechanics, flux also quantized as if like charge is quantized. So it is we can define the filling fraction mu that is just given by number of Landau levels field. So this is just we can find by total density of electron divided by the degeneracy of the Landau level. So it is given by this, and there is a first some scientist Laughlin proposed a trial wave function for these states, which have been formed like 1 by m type, like 1/3, 1/5, 1/7. For this type of fraction, he proposed this type of many body wave function. It contains all the particles coordinate, and here this m basically odd number. So this theory is like incomplete. It cannot explain all the fractional state. That's why we need a different approach. And another proposed by composite fermion theory, proposed by J.K. Jain. He basically introduced a quasi-particle. It's known as composite fermions that are bound state of electron and even number of flux quanta. You can assume that all the electrons they attach some even number of flux quanta from the external magnetic field, and they form a new type of quasi-particle. And with this help of this quasi-particle, we can explain this fractional quantum Hall states. So we can say that these quasi-particles experience a reduced effective magnetic field. B is the external magnetic field, and this B star is the experience by the quasi-particles. So it is just given by B minus 2p rho phi 0. And so also in this reduced effective magnetic field, these new quasi-particles also will form some Landau level type of energy levels, and their filling fraction also, if we express it by nu star, then we can relate this nu and nu star from this formula. So it is given by here. So here, if we take this nu star some integer number like 1, 2, 3, then we can have different fractional values of this nu. Like for this schematic diagram I shown, when nu star is 1, like n is equal to 1, that is 1 Landau level is filled, then we can have nu is equal to 1/3, like t is equal to 1. If we just take an n is equal to 1, t is equal to 1, then we have nu is equal to 1/3. Similarly, if there are 2 Landau levels filled, then we have 2/5 filling fraction, and when 3 Landau levels filled, we have 3/7. So using this picture, we can explain the most of the fractional state observed in experiment. So here numerical techniques are used, like firstly, we cannot determine the many party wave function for the fractional quantum Hall state. That's why we are taking the help of the composite fermion theory, and we map our system to weakly interacting composite fermions, and then we find out their wave function. That is just a Slater determinant of single particle's wave function. Then we multiply it by a factor to take into account the interaction part between the particles. Then we get the total wave function for this fractional quantum Hall. So it's a little tricky actually. I'm not going about details of the term. So basically, we just consider like spherical geometry. We consider like all the particles, like correlated electron systems. These are resides on the surface of the sphere. So that becomes a 2D surface, and this have a like a why we are using this spherical geometry, because it don't have any edge state. Like it will be an edgeless 2D surface. And we just consider a magnetic monopole is kept inside the sphere, and that produces the flux, and that is the coming source of the external field. And then we can find out the ground state or excited wave function of the state. Like first we have to take the Slater determinant of the single particles, that is single composite fermions. Then we just multiply it by the interaction part. Then we project all the particles to lowest Landau level. So that's the main thing. So in this system, basically we can study collective excitation. Like here, exciton means if you we can see exciton means some pair of particle and hole. So here also, just this is the first figure. This is the ground state of 2/5 filling fraction. 2 Landau levels are filled. So if one particle just goes from first Landau level to second Landau level, or 0th level to second Landau level, this type of transition can happen if the system is part of somehow externally. So mainly this is a collective phenomena. Which particle will go this transition, and also 2 or 3 particles can excite all together. So this is a basically not a single particle phenomena, so a collective nature, and so we can study this type of excitation in this system. And this also, if the system contains like 2 species, like spin up and spin down state, then also there are some 2 types of Landau levels is there. So here it is shown for 3/7 filling fraction, And also transition can occur from up spin to down spin. So this type of excitation is known as spin reverse excitation. So when the system contains only one spin component, we can say it's spin conserving excitation. And when there is just a flip of some spin, then we can say spin reverse excitation. So basically, I studied this type of excitation in my fractional quantum Hall state. So now I'll just explain uh, how we can find that fractional quantum Hall effect in rotating DC system. Just consider like what I explained earlier slide, like some Bose atoms are confined in a 2D plane and the whole system is rotating about Z axis. So in this system, we can write down Hamiltonian like this. The Hamiltonian contains system's particle energy, kinetic energy, and this is the harmonic potential energy, and this is the rotational energy, and this is the interaction between particles. So in this system, if we take or if we choose the magnetic vector potential in such a way, like that corresponding magnetic field is perpendicular to the tapping potential. So we can have this, we can just re-express this Hamiltonian in terms of magnetic vector potential. So it is can be re-expressed like this second line. So here we found that this term exactly looks like this first term, 1 by 2 mp minus a whole square. This term exactly looks like some charged particles are there in presence of magnetic field. So there is a possibility of formation of Landau lasers and also possibility of quantum Hall effect. So in this by this way, in this rotating Bose system, we also can study fractional quantum Hall effect. Uh, Although it is just theoretically predicted till now, up to date, it is not experimentally realized. So I just studied also this type of state in my PhD work. So also we can just assume these two, if these two omegas are same, then only Hamiltonian contains interaction energy. Since this is a strongly interacting system, that's why we can say that kinetic energy part is quenched or kinetic energy becomes a constant part since Landau levels energy is a constant term. So we can just have the interaction energy is the more prominent in this type of system. So we also can apply this composite fermion theory to this Bose system. Like here, the difference is that we have to consider the Bose atoms attach odd number of flux quantum, not even, to make this composite particle as fermion. So same theory, composite fermion theory applied in Bose particles. So they also experience a reduced effective magnetic field, and we can relate these two filling fraction by this formula. And if we take different values of these n and p, we can have different fractional values of this mu. Like if we take n is equal to 1 and t is equal to 135, then we can have half 1 by 4, 1 by 6 filling fraction. So here are some techniques to find out the ground state and excited state. Uh, as I said, firstly, we have to take the Slater determinant of the composite fermions, and then this is the interaction part, then some projection operator we are taking. So this is for ground state part, ground state wave function. And for excited state, similar thing, we have to take a Slater determinant, and just one particle goes to the another transition occurs to another spin state, and some coupling parameter is added here, that is actually basically Cleb's Jordan coefficient to take into account the angular momentum of this state, and rest is the same, this is the interaction part and projection operator. So if we know the wave function of the system, then we have to know only the what will be the interaction between the particles. So I already said the both atoms interact with each other via the contact delta function type potential. So, but basically, I studied by Monte Carlo method. So this delta type potential using in Monte Carlo simulation is difficult, and also it needs high computational resources. That's why I taken this type of potential between these Bose atoms. Like it has a form like 2 mu by cos hyperbolic square mu Rij. So this is basically it is the plot of this function. So it has a tuning parameter mu. We can change the values of mu. It basically tunes the range of interaction. When mu values are higher, like 3, it behaves like contact interaction or delta function type. But when mu values are lower, it is basically defines short range interaction. So our superiority for this potential is we just can change the range of interaction. So in using this type of potential, I calculated some energy spectra for spin conserving excitation. Like this type of possible lowest excitation, I just considered in my study, like from transition from 0 to 1 state, 0 to 2, 0 to 3, this type of excitation. And then I calculated the energy gap, that is excitation energy minus the ground state energy. So here psi k is the excited state wave function and psi g is the ground state wave function. So here is the result for this excitation spectra. You can say this spectra means like a dispersion curve for energy as a function of momentum. If there is a plot. These results are using a Coulomb long range Coulomb type potential, and these are using this Poisson-Taylor interaction. And we just varied the values of mu. And this is for 3 fraction half 1/4 1/6. I calculated the energy gap between excited state and ground state. So here we found some Roton type of minima is observed in this type of excitation that are known as Roton minima according to the Feynman superfluidity theory. And also this for short range potential also we found the Roton minima nature. And another thing I did spin reverse excitation. That is I taken 2 species of spin is there, and it may goes to one state to another state. Basically, here pseudo spin half state is considered. Basically, boson has uh, like odd spin like one. So we have to take 3 species, but here we taken only 2 species. Like we just consider like both atoms have pseudo spin half state only. So they have like plus half spin and minus spin. So there's this type of possible excitations we consider, and this is the spectra for the spin reverse excitation for half 1/4 1/6. So here we find that for spin reverse excitation, the curves are showing some positive dispersion. That is, it is increasing nature. So it basically this type of dispersion curve are known as spin wave nature, and these are observed in a ferromagnetic system. So it supports the ferromagnetic behavior. And final conclusion. So there are some key takeaway messages. So we just seen that these many body systems it reveals how simple particles interacting with each other, they give rise to rich emergent phenomena. Also, BC represent a milestone in quantum statistical mechanics, deeply linked with atomic, condensed matter, and optical physics. And also, both Hubbard model captures the essence of quantum phase transitions like superfluid to Morse insulated transition, and BCBCS crossover that bridges between bosonic and fermionic superfluidity, and that relates between the quantum fluids. And also, fractional quantum Hall effect is a prime example of strongly correlated topological matter, and with fractional statistics and novel excitation. I have to mention that fractional quantum Hall effect is a topologically protected state. It does not depend on the geometry of the system. And also dipolar BEC and rotating BEC system that extend these ideas into new quantum phases like super solid and also quantum Hall-like analogy. So that's it. Here are some of my publications related to sectional quantum Hall effect in rotating Bose system. And these are my collaborators. And this my research interest strongly correlated quantum system like fractional quantum Hall effect, Bose-Einstein condensate, and also topological nature of quantum liquids. And thanks for listening me. And please ask me some if you have any questions.
I want to thank Dr. Momita Indro for her excellent talk. She covered almost all the theoretical and experimental development that had been occurred in this field over last 3 decades. We feel really proud. She was our student. So now the question answer session. So due to shortage of time, I can take few questions from the participant.
Yeah.
You may ask the question or you may write the question. So Momita will answer.
Yeah.
So there is a question from Shumon Kumar Pal.
Yeah. For many body wave function for BEC should not we symmetrize the wave function for having motions. If we do so, we should have some exchange energy configuration. Can you please just unmute yourself? What do you mean to say? Is it really?
Yes.
Hi, Shuman. Please tell me what's your queries.
So at first, while considering the interactions for BEC, you written the Hamiltonian, the slide,
Yeah.
and you written that from mean field theory you got the wave function. You just keep the product state of the orbitals, and I'm telling that if we have bosons, have some then under exchange the state shouldn't change. So I'm telling that shouldn't
You
we?
are telling about this like many body waves.
Yeah.
Yeah,
So
that's basically mean field approach. We cannot write like this, but mean field according to the mean field theory, we just approximated like total wave function can be written like that. But in quantum droplets, like when systems are interacting, interaction is more there, then we cannot write like this. We also add some another term like, that is known as LHY interaction. This is according to the name of 3 scientists, Lee, Wang, and Yang. So you may just visit that LHY interaction or LHY correction part. That is actually we have to take into account in case of quantum droplets or for interacting system.
okay, I will look into that.
Clear?
Okay.
Yeah. Okay, any other question?
Is there any more question from the participant?
I have a one.
Okay.
Yeah. Please.
Myself Surya Ghosh, Bijoy Narayan Mahavidyalaya student, Physics department. My question is all type of matter particle can change into BSC, or there is some specific type of matter particle that only can be changed into BSC?
For BC, of course, the atoms should be bosons. Like they should have uh, like integer number of spin, total spin, that is like nuclear spin and atomic spin. This sum of this spin, nuclear spin, should be odd integer. It should be bosons. Then this BC can happen. And for some atoms, there are some technical issues, but for like both type of particles, it can be possible.
Okay,
Just
thank you.
need some ultra cold temperature. No.
And I just say something on this. So mostly the boson means mostly the neutral atoms. I mean, neutral alkali atom. All the experiment done on the BC is on neutral alkali atom. Otherwise, it is very difficult to deal with.
Yeah,
other.
difficult due to the technical like
Need
experimental
to
problem.
very
Like
state.
all the atoms cannot be cooled to by laser
Yes.
cooling and all.
By
There are
laser
some difficulties. Yeah.
That's why it took probably 74 years to 1924 to 1995. So it's such a long period. So it was a challenge to reach that. Okay, so if I think we should stop now. So if there is no more question, we can go to our next speaker. Now we move to our second talk. Okay, so again, thanks Momita for your excellent presentation, starting from
Yeah, it's difficult actually for undergraduate student. These topics are not quite easy.
You
So I
covered
don't
everything.
know. Yeah,
No,
basically
everything.
I
Last part maybe,
tried.
but before that, the every part is very, very, very good. So last part may be
Yeah.
difficult for the
Just
students,
one
but
request, if you can drop me any email if have any student have some queries and all. So we can just talk later also.
very good.
Yeah,
So
thank
so now, now we move to our second talk from another promising young experimental physicist, Dr. Orpita Dash. I think Orpita is here. So she will talk about trimming the cold, creating and exploding ultra cold molecule in quantum lab. So now let me introduce Dr. Orpita Dash. It is my pleasure to introduce Dr. Dash. She did her MSc from University of Calcutta, then PhD from Shah Institute of Nuclear Physics in the field of light matter interaction, experimental. Then she moved to University of Innsbruck for her first postdoctoral research work. She spent there 2 years working in the field of ultra cold atoms and molecules. Currently, she is a Newman fellow working with Professor Simon Cornish in the field of ultra cold molecules. Orpita is joining us from Durham, UK. Orpita?
Yeah.
Uh,
Can you hear me?
yeah, I can hear you.
Okay.
Okay. So now stage is yours. You can start.
Okay, let me share my screen first.
Yeah.
I hope you can see my screen now.
Oh, yes, it is coming. So
Okay.
now.
Okay.
Yeah.
Okay. First of all, I want to thank you for this nice introduction, sir. And it's my pleasure being invited by you to speak about our research work, or you can say like, I learned from you during my master's, the basic phenomena, and then now I'm going to explain how we can do this in our lab. So this 2025 is the International Year of Quantum Science and Technology, and it's a great time to talk about ultra-cold atoms and molecules, a field where quantum physics comes alive in the lab. So in the past decades, 2 Nobel Prizes have recognized big milestones in this area. One in 1997 for cooling and trapping atoms with laser light, and another in 2001 for creating a Bose-Einstein condensate, a new state of matter. So today or nowadays, we go even further. We cool atoms and molecules to nanokelvin temperature, control their motion and interactions, and use them to study quantum system. So in this talk, I will show you how we cool atoms, trap them, and use them to learn more about quantum science. So to understand ultra cold, why we care about ultra cold atoms, we first need to know or need to ask ourselves, what is temperature here? Here, the temperature means how fast the particles are moving. So the temperature is a measure of random motion of particles. So it's a kinetic temperature. Now, as we cool down the atoms, their motion slows down, and when we go to very low temperature, for example, microkelvin or even nanokelvin, something amazing happens. All the classical behavior of the system taken over by the quantum effects, and these atoms behaves like individual particles and start acting together. So this gives us an unique opportunity where we can create and control quantum matter, and we can tune them. We can like their interactions, how they move, and even what kind of quantum states they form. So we basically can tune the interactions, the geometry, and the dimensionality of the system. So going ultra cold is not just making things cold, it's about entering a new world where quantum physics become visible and controllable. So why we interested? Because following all the recent developments in laser cooling, trapping, and of course in atoms and molecules, we can use this system as powerful tools to study fundamental quantum physics, quantum computing and simulation, precision measurement, and quantum chemistry. Now, so how we cool atoms with light? So we use basically the phenomena called Doppler cooling, where we shine a laser light to an atom or atoms, where when they interact, like the atoms interact with the laser exerts force via photon momentum. So what happens, like, for example, you consider a two-level systems of atom, and you have two counter-propagating laser beams, which are red detuned, means the frequency of the laser is less than the transition frequency of the atoms. So now, when they interact with the atom, the laser exerts a force on the atom. So we know the atoms are in general, the atoms in gas state, they are moving. So for example, if the atoms is moving towards this left laser, so let me take my laser pointer. Yeah. So atoms moving to the laser 1 state, then a laser, it get easily absorbed by this laser 1, and then it's emit a photons, and that's why the atom's momentum, like it kicked by the laser, so atoms motion got reduced. Similarly, if the atoms moved rightwards, it will absorb by laser 2, and the same phenomena happen. So it get again a kick and its motion get reduced. So by this kind of shining the laser, you can basically freeze the motion of atoms in a space. Now this is only two lasers, so you can think we can only reduce the motion in one space, but we need for 3 direction. So to do that, we shine lasers in all the 3 directions in atoms, and in later my slides I will show you how we do that, like I will explain. So we shine all counter propagating lasers in 3 directions, so there are 6 lasers, and with that a kind of force we can light it. It generates a damping force, which is basically depends on damping constants. All laser parameters and the atomic parameters are there, like their natural line widths of the atoms and the detuning of the lasers. So with this, we can only move in a velocity space. So this viscous force slows them down, like moving through a thick molasses. You can consider like a fly stuck to a molasses or a jaggery. Then it's trying moving through the jaggery. So it looks like kind of viscous, but it's not completely freeze. So it's freeze in a velocity space. Now we need to freeze them into the the position space. So to do that, we apply a position dependent magnetic field, where then in this damping force, you can basically add another damping parameter, which depends on the position. So we basically applied a magnetic field, where now all the energy levels of the atoms is non-degenerates, and you can transfer the atoms. So it basically reduced your motion, and as well as it can stuck you in a position space. So all this phenomena of this Doppler cooling, you can think about like you are running towards a headwind, so your motion got freezed. Now, what kind of atoms we choose? Of course, we choose a simplistic atom, because if you have like more electrons in your outer cell, it's really hard to control. So the as you heard before, so we use kind of alkali atoms, neutral atoms, which has one single electron system at the outermost cell. So this is so rubidium is very famous in this field. So rubidium, this is a level scheme of rubidium 87 isotope, and we basically work in the hyperfine states of the rubidium. So this is a D1 line I'm showing, but actually we use D2 line, so there will be more hyperfine states. And we use basically when we use two laser light to cooling, one transition from ground state to the maximum excited state, and another one is from the groundmost state to the excited state, because when you shine a laser, then your atoms got absorbed, but when they decay back, they can decay back. For example, you shined a laser from F equals to 2 to F equals to 2 excited state, then atoms can decay to F equals to 2 and F equals to 1 also. So when they decay back, so then you can lose your atoms from your cooling cycle if they decay to F equals to 1. So get all the atoms back to your cooling cycle, we shine another laser from F equals to 1 to F equals to 1, so that any atoms going here in F equals to 1 ground state, they can bring back some like in the full cooling cycles to F equals to 2 state. So this is a Doppler cooling. With this, we can reach around hundreds of microkelvin temperature, but we need to go beyond this Doppler cooling because all this there is a Doppler limit because of the line width of the atoms. So you can't go beyond this temperature. Like, for example, for rubidium 87, it's around 144 microkelvin. So to go beyond this Doppler cooling limit, we use a technique called polarization gradient cooling or the Sisyphus cooling. So where you have a light whose polarization varies in space, and that's why it shifts the energy levels of the atoms differently depending on the position, like due to AC-Stark shift. So how we create that? Basically, we shine two counter-propagating lasers with, for example, linear. The laser polarization is linear, but they are orthogonal to each other. And thus, when they interact, like they superposed, the polarization over the space could be sigma plus, pi, sigma minus, and you then the atoms feels this kind of various different polarization of the light, and depending on that, they can transfer from one state to another state. And so the atom moves through this field, they get optically pumped into higher energy states. Like, for example, atom was here, so it pumped to the higher excited state here, then it's decay back to the lower excited state. Then again it comes back and it pumped into the higher excited state, it decay back to the lower excited state. So thus the atoms lose their energy when they fall back, and this is the cooling mechanism here. So it's called a Sisyphus cooling because, just like a myth, atoms keep climbing uphill to fill back again, slowly draining their kinetic energy. And this lets us cool them well below the Doppler limit and reaching the recoil or even the subrecoil temperature. So now, as we move to the final stage of reaching ultra cold temperature, which is evaporative cooling. So the idea is simple but powerful. We remove the hottest atoms from the trap, and remaining atoms collide and thermalize, reaching a lower temperature. So you can consider, like, you have a cup of coffee or tea and it's very hot. So what happened, like the hot vapor are basically going upward from the surface, and if you keep it as it is, then after a few times your coffee or tea gets cold. So it's a kind of that. So you just remove the hottest atoms from the trap, and then the remaining atoms thermalize to the lower temperature. So the trap means here we can form the trap by optical beams. We can form the trap by magnetic field. So there are various kind of trap we can use. Generally in our experiment, we use optical trap and the combination of the magnetic trap. So it's a kind of hybrid trap. And when we are doing the evaporation, we basically lowering that trap depth. So it's a let's say after polarization gradient cooling, we have this much atoms and the trap depth in an optical dipole trap. And then we just lower down the trap potential. So what happens, like all the atoms which was up there are basically going away from the trap. So you can at last you can have only small amounts of atoms in your trap which are very cold. And because it's at the lowest state of the trap, you can consider a optical trap as a harmonic potential. So it's a ground state of the harmonic potential at that time. So it has lowest energy. So this is the regime where the Bose-Einstein condensate begins. So the idea is like that. So you just evaporate, or you just lowering down your trap depth, and then you can see your atomic distribution transforming from Gaussian to the Bose-Einstein distribution. So why this matters? Because this enables transition to the quantum degeneracy. And here we can achieve the temperature about 100 nanokelvin or below than that. Now, what is BEC? So I think I don't need to elaborate more because our former speaker, Momita, already explained this very nice way. I just want to explain in a brief way so that we can have a flow here. So what is Bose-Einstein condensates? So Bose-Einstein condensates basically when we dilute the gas of bosons which cooled below a critical temperature. So this is a Bose-Einstein condensate, and this is the density distribution of the atoms we have. And this depends on there is a critical temperature which depends on this density distribution. So when we lowering down the trap depth, is basically reducing we are changing the density of the atoms, which we called phase space density, which related with the total atomic density and as well as the temperature of the system. So when we cool the gas below this critical temperature, a macroscopic number of particles occupy the lowest quantum state, as I show you in my previous cartoon. And then the system undergoes a kind of quantum phase transition to form the Bose-Einstein condensate, where all particles behaves as a single coherent quantum object. And below this critical temperatures, atoms are no longer distinguishable as classical particles. So Bose-Einstein statistics dominates, and many atoms pile up in the ground state. So here I'm showing a lab picture of the the absorption image of the atoms, how it's transformed from thermal gas to the BEC. So when we have around a few microkelvin temperature, we have this thermal gas and the distribution is Gaussian. Then we decreasing our trap depth, we can clearly see it's basically changing the this distribution, this Gaussian distribution, from this sharp peak distribution or the Bose-Einstein distribution, and it basically surrounded by here at the lowest part like thermal gas. And then when you go beyond this limit, it's about when this feature we can see when your temperature of the system is more or less equal to the critical temperature. Then when you go beyond the critical temperature, you can see a pure BEC where you have the sharp peak of your atom distribution, and it looks like very nice atomic imaging, like absorption imaging. So yeah, so at this chemical, when we go below this critical temperature, the ground state occupancy grows rapidly. And so this is a kind of basic concept how we do the cooling of atoms in our lab, but these are not like, we just not need only the laser lights. We need a very high, ultra high vacuum to get this kind of cold temperature. So our silent hero is the ultra high vacuum. So preserving these ultra cold conditions, we need, like, the background gas atoms can collide with the ultra cold atoms. They can eject them from the trap. So we need to remove all unwanted atoms from our experimental cell. Then even a single collision may destroy this Bose-Einstein condensate. So we have to be very sure that there is no other atoms or any particles other than the atoms we want to cool. That's why we need this ultra high vacuum. And also this requires to reach long lifetimes. And for that, we need an ultra high vacuum of the order of 10⁻11 torr, and which means fewer than one background atom per centimeter cube. So lifetimes of tens of seconds or 2 minutes are needed for this precision measurements or precision experiments. That's why we need this ultra high vacuum. And this will enable the quantum experiments, like, because this cooling is time consuming, so we need the stability. And the good vacuum ensures coherence and rapid repeatability in quantum control. So we need this ultra high vacuum other than the laser lights. And then, so here I'm showing a small part of our experimental table. So this is our optics table. And you see there are loads of optics here, like starting from mirrors, lenses, web plates, post, okay, everything. And here you see this one, like this is our pump, which do the vacuum for us, like at order of 10⁻11 torr. And inside this, I'm sorry, this is not much visible here. So you see this white part here. So inside that there is a glass cell, like a rectangular glass cell, where we prepare the atoms. So we start from a dispenser, which has a kind of metal, and we induce current there, and which can eject basically rubidium atoms or whatever atoms we need, that atoms. And then we basically, that's in a gaseous state. So then we do this laser cooling and trapping inside this glass cell. So this is a kind of experimental overview, although it looks a little bit simple here. It's not that simple to get the laser cooling and trapping. So
Orpita,
another thing, yes,
Orpita,
sorry.
Sorry to disturb you. This is the dipole BEC trap or double mud BEC trap? I think this is dipole
Okay,
BEC
so
trap.
this one is my current experiment setup. So this is a two species more like atom trap actually. So there we started from two dispensers, rubidium and cesium. And then we have a pyramid mode, which is a second, like first phase cooling. Instead of G-men slower, we have that. And then we push, like that part is not showing here, which is inside here. And then we push those little, like the rubidium and cesium atoms inside this glass cell. And then here we do basically all like magneto-optical trap, then loading into the dipole trap, evaporation cooling, and other stuff also.
Okay. Okay.
And
So,
here, like in this
what
direction,
dipole
there
laser
is
are you using? What wavelength dipole laser are you using?
Okay, so for our case, we use 1550 nanometer wavelength, but people also use 1064 nanometer. So these are kind of common dipole trap laser.
So carbon dioxide laser or something else?
No, it's like very high, but it's not carbon dioxide one.
Okay. Okay, let's continue.
Yeah. So this is like in this direction, we have a camera. So our probe beam, which do the imaging, is send it from this direction, like from top and then like this. And then we click the images by that camera, which I show you before, the images of the absorption image of the BECs. Okay, so as I say, not only the lights, not the vacuum, and then there another important parameter is the timing control, because this is very, very much essential to control all this like light on, light off, magnetic field on, magnetic field down, trap depth reducing. This all needs a very, very much control timing. So to do that, we use basically programmable field is gate arrays, so FPGA or digital timing systems coordinate hundreds of events by perfectly with a proper program. And we also need stable laser intensity and frequency, so cooling efficiency and how like the trap depth where we can trap the atoms on keeping laser power steady, while frequency locks ensure the lasers stay tuned exactly to the atom's resonance. So we use devices like AOMs, acousto-optic modulator is a kind of optomechanics, electro-optomechanics device, electro-optic modulators, which in short we called EOMs, to help us quickly adjust this laser power and the frequencies on as we go carry our experiments. So why does this all matter? Because to create things like Bose-Einstein condensate, we need very reliable and repeatable conditions over a long experimental cycles. Even a tiny drift in timing or laser settings can cause us to lose atoms or fail to achieve condensation. So precision is a key to success here. And as you see, like I forgot to mention that one thing, this timing things is not in seconds, is in like microseconds or 2 millisecond range, or sometimes it also comes to like we need to control a pulse, light pulse of the order of nanoseconds. So you understand how good timing control we need to do this all kind of experiments. So what I'm going like trying to say, like all this experiment does not only include the sense of optics, this also includes sense of handling high vacuums and also electronics, and of course the quantum physics is there. So it's a kind of very diverse field. So here I'm showing a just an example of timing sequence, which we use generally to get like ultra cold atoms in optical lattice. So this is a kind of, like you can see, it's of the order of 8 seconds. We have already atoms in optical lattice. So yeah. Now, with the precise control over timing and laser parameters, we can create more complex and versatile setups. One powerful tool we use is the optical lattice. So a kind of light crystal formed by interfering laser beams. So for example, there is cold atom, and then we shine a LED to counter propagating laser. What happens? It will create a standing wave. you all know from like basic physics course. So when you have two counter propagating like kinetic wave, you can create a standing wave by superposing them. So it's the same concept here. Although when you do that, then it forms a periodic potential, as our former speaker Momita already mentioned. It forms like egg cartons for atoms, where you have like a dip and peak, and in each dip we basically our goal is to put one atoms in each peak, each dip. So you can see here like all the atoms, one atoms in each peak dip. So this kind of things looks like a electron in a solid. So then how I'm going to now say how, okay, we shine only two laser, counter propagating two laser to the atoms. It will create only 1D lattice, and the atoms will see it's like a pancake. So atoms will go from here to here. It will distribute like in a pancake shaped geometry. That's I was in my previous slides, I was mentioning like we can control the geometry of the atoms, of the system. Thus, if we want to get a pancake-like system, we use 1D lattice. Then you shine 4 counter-propagating lasers, so like two orthogonal direction. Then you will get a 2D lattice. What atom will see is a tube. So you basically freeze the motion, or you trap the atoms in a 2-dimensional space. So it can only move, only have one free direction. That's why it looks like a 2D tube. Then you shine the lasers in all 3 directions, like counter propagating 3 directions. You form a 3D lattice, and then it looks like a crystal. So we call this a light crystal of atoms. Now that we have reached the regime of ultra-cold atoms and achieved Bose-Einstein condensation, so we can go one step further using these atoms as building blocks to simulate complex quantum system. One powerful example is the Bose-Hubbard model. Already you have well explained about explanation about Bose-Hubbard model, but I'm just going to say how we use this in our experiment, or how we can exhibit this Bose-Hubbard Hamiltonian in our experiment. So this term, the first term, is the NN hopping, like site-to-site hopping term, where we can basically control the parameter, how it can hop between one side of lattice to the another side. Then there is this on-site interaction term, where we can control how the atoms interact when they are in the same site. And this is the on-site energy. So in these things, the good, the best, or the simplest way, or the first things we want to see with this Bose-Hubbard model is to see superfluid to Mott insulator transition. So when you have the BEC and you load the BEC at state of the atoms in an optical lattice, you will get a superfluid state in a shallow lattice, let's say, where when this tunneling terms is dominated over the on-site interaction term. So you will have a superfluid state, so you can't localize the atoms. Atoms could be somewhere in the lattice site, and it contains a phase coherence. So when you detect the absorption image of the atoms, you will see a interference pattern due to that. And then if you turned off your lattice potential, so you are going from a shallow lattice to the deep lattice, then you are in a regime. At a particular point, you will be in a regime where your on-site interaction will dominate over the tunneling term. And you will then all the atoms who were distributed somewhere in the lattice site will go to the particular lattice site. And now in this state, you can pinned atoms to the lattice site. So it's a, you can localize the atoms. So this is called the Mott insulator state. And here I'm showing an experimental image, how we did in our lab. So we basically, by time, we increased the lattice potential. Basically, we turned up the lattice laser power. We have to have that control, what I just said, that we control that by AOMs. Then those AOMs basically controlled by some other electronic circuit, which basically stabilized when you turned up in a very quickly. So it can't be that fast that it just blow up. So it could be stabilized in that power or intensity. So when there is no lattice, you see pure BEC. When you turned up your lattice and the lattice potential is not that high, so intermediate, you will see a superfluid state and you see this interference pattern. Then you turned up your lattice again, it goes high enough, then you see this superfluid state. And after that, if you again decrease your lattice potential, you can get again back your superfluid state. So these things we also use now in our labs to see if our lattice is working properly or the BEC we made is a pure BEC or not. If it's a pure BEC, then this phase coherence remain same when we turned down the lattice. So nowadays we use these things to calibrate our system, or to understand if our system is working fine. So this opens up an opportunity to use cold atoms in lattices to simulate complex quantum system, and we can model condensed matter physics and also quantum magnetism. Now, I just say we observe Bose-Hubbard model, or we basically exhibit Bose-Hubbard phenomena in the lattice. Now, I'm now going to say we can also see wave nature of atoms in our system, and which is called Kapitza-Dirac scattering. What is it? So when a standing wave of light acts like a diffracting grating, atoms behaves like a wave and diffract, much like a light on a crystal. So it will diffract, and you can see a diffraction pattern from like bright fringe to the dark fringe here. So how it works, we apply a short laser pulse in 1D optical lattice, and then cold atoms diffract into multiple momentum states, and each diffracted peak corresponds to an integer multiple of 2h bar k momentum. And why it is interesting? Because it will give you direct visualization of matter wave interference, and this demonstrates also atom light interactions in the momentum domain. And we use this phenomena in our lab to have like a check probe coherence, band structure of the lattice, and the lattice calibration. So here I'm showing our like last year lattice calibration results. So when we do these things, we see this much like this is so for our understanding, like I just point out this point first. So this was the single atoms, like the BEC. And when we shine the, start applying the short pulses at a particular time, which I mentioned here, like marked here, we see that this kind of all diffraction pattern here. So if your lattice alignment or like depending on all like the timing controls and these things are very good, you will see much and much a diffraction pattern if you go like beyond more than 100 microsecond pulse time. But for our case, we don't need to go there. We just need to have this few order of diffraction to just have to do the lattice calibration. So from this fitting, we extract the lattice trap depth, and from that we calculate the lattice like laser beam waste. So this kind of, because all your trap depth depends on the intensity depends on the power and the laser radius, you can say. So with this, like, I think I hope I can convince you that we can use atoms and light to form a light crystal, and we can do some like condensed matter physics or quantum magnetism with this system. So what we gain, do we gain in this system, and what do we lose in this system then, like over the normal solid state system? So we can have 1,000-fold magnification, so possibility to detect particles individually, slowing down of dynamics, which is easier to observe, like millisecond instead of picosecond time scale. But we have to go very, very low temperature, which is challenging to get that, which is like ultra cold quantum gases of the order of less than microkelvin. So you have to have in the nanokelvin region. Then the interactions here is local. So you need to pick or need to play a trick to obtain long range interactions. So in my next few slides, I'm going to introduce you what kind of platforms we have for long range interactions. So we have ion traps, like ions in ion trap, where you can see the long range interactions, and the people, like, there are all over the world, there are various groups working in the ion traps. I'm just highlighting a few. Then we have magnetic dipolar atoms, which have magnetic moments, and which is very, very much also interesting to study these long-range interactions. Then we have Rydberg atoms. If you trap the Rydberg atoms in tweezer, so tweezer is just a focused beam, so it can behave like a tweezer and it can trap one single atom in the trap. Then we have atoms. We also have atoms in cavities. So if you trap atoms in optical cavity, you can have like exhibit the long range interactions. And what else we have? We have ultra cold polar molecules. For our case, or in my in my recent or current research field, I'm working on with this ultra cold polar molecules. For our case, I'm working in rubidium cesium molecules. So why this is fascinating or important for long range interactions? Because, as you know, like, molecules are rich in physics because you have rotational degrees of freedom, you have vibrational degrees of freedom. On top of that, this kind of molecules have electric dipole moment. So this gives us to study precision measurement and ultra cold chemistry. And then you have these molecules have like long range dipole-dipole interactions. So with this, you can also venture the field of quantum simulation and quantum computation. Now, what advantages of these polar molecules have? as I just said, this long-range interactions is comparatively very small, very strong. This long-range interaction is tunable. You can tune the long-range interaction, and how I will explain that. The long-range interaction is angle dependent, so it depends on the orientation of your molecules. So if you if you change your orientation of the molecules by applying some electric field, you can tune the long-range interaction also. Essentially all the control techniques that have been demonstrated on atoms can be extended to the molecules, and dipolar molecules are long-lived. And I just want to highlight to you, like in last year, a group from Colombia, it's Sebastian Will's group, they achieved sodium cesium molecular BEC. So it's also like kind of milestone, achieving milestone in the ultra cold dipolar molecules field. But we have challenges. So nothing's come free. That's why. So molecules are not readily laser coolable. All molecules are not laser coolable, or you can cool them, but laser are not available. Molecular samples might not be stable in 3D geometry. So molecular scattering is not fully understood. It's very complicated. Molecular preparation strategies are comparatively complicated than the atoms. So for example, I will show you how we do in our lab. So we use double species setup, and we detect those atoms, like how many molecules we have. We detect that in a kind of tricks that I will also explain in next slides. So this is highlights from that sodium cesium molecular BEC. So they achieve like 6 nanokelvin temperature with of sodium cesium molecules. Now, what are the possible candidates for these polar molecules? They with the strong electric dipole moment and heteronuclear structures and low vibrational state, there are loads of molecules, and all over the world, people are working with the various kind of species. And in our group, in Durham, we are using rubidium cesium. And also in my previous postdoctoral group, I was working in Innsbruck with Hans Christoph Negrel, and there I got introduction of rubidium cesium molecules. And so these kind of pairs are making through the association of ultra cold atomic gases, and these pairs can be they prove they can be can be cooled directly. So the lasers are available to do the direct cooling of these molecules. And here I'm showing like why people are interested in different molecular pieces, because their interaction strength is different. So you have different dipole moment for different molecules. So where rubidium cesium is intermediate, so it's easy to handle. More dipole-dipole interaction is also sometimes bad to get to control them. And sodium cesium is like one of the topmost candidate here. And there is the topmost one is lithium cesium. Now, as I said, like from this picture, you can understand how the dipolar molecules span an enormous range of energies due to their rich internal energy levels. You get additional degrees of freedom in terms of vibration and rotation, even in simple diatomic molecules. And we are particularly interested in rotation, utilizing the rotational degrees of freedom that leads to a beautiful ladder of the long-lived states in the molecules. So here I'm showing just 3 rotational states of rubidium cesium molecules with magnetic sublevels. And So here the first number is N state, like the rotational state, and the second number is the Mn state, the magnetic sublevel state. And it's possible, like you can couple, like conveniently connect this electric dipole transitions, like from this rotational state to this rotational state via microwave, because this is about a 2 gigahertz where microwave could work. And thus you can form a playground where you can encode spins or qubits, and you can use this simple spin half encoding to extend a couple of multiple levels to engineer. It's called synthetic dimension, where you don't have any other trapped or something like that, but you still can have form a trap with this with this ladder type of systems. So it's called synthetic dimensions. So in this, like this paper, from our previous group members, they showed how you can connect all the ladder type rotational states by the microwave. One important thing to note that these molecules also have hyperfine structures associated with the nuclear spins. So for example, for rubidium cesium, only this ground states has 32 states, hyperfine states. And we can utilize these hyperfine states also to encode or storing quantum information. In this paper, they showed how you can use or utilize this hyperfine state to store your quantum information information in the states, and the coherence time you can achieve, which is of the order of 5.6 seconds, which is more than enough to study the interactions of in this region. Then the one big motivation for these molecules is the, as I said, dipole-dipole interactions. So how you can like tune this? So we can tune the dipole-dipole interactions either by tuning the dipole moment with application of electric field, or by applying microwave field between several rotational states, where we can study spin exchange interactions via transition dipole moment. We can study the quantum magnetism with molecules confined in the optical traps, like optical lattice or optical tweezer. And this is a XXZ model, a spin model, where you can study this interaction strength by measuring the dipole-dipole interaction strength, because those are related. So, but here the complicated term, like when you want to do study this, you want to basically exhibit a phenomena who has the energy less than 1 kilohertz, but your molecules are trapped in a optical trap who can give a AC Stark shift of the order of 200 kilohertz. And then you can't exhibit, can't observe that 1 kilohertz interaction region. So to get rid of that AC Stark shift, we played a trick. We find an optical trap for our molecules, rubidium cesium, where at particular laser frequency, the polarizability, which is mainly causing the AC Stark shift, is equal for all the rotational states. So we use that particular frequency of laser to create this optical lattice or tweezer where we trap our molecules. So how we prepare the ultra cold molecules? That's a kind of next things. So as I mentioned, you can first make molecules and then you can cool it down, which is like the direct cooling, following the normal laser cooling and trapping technique, as I mentioned before. Or you can cool the atoms separately or simultaneously. Then you make molecules. How we do that? We make molecules by, with the help of Feshbach association, which is a magneto-association, and then followed by stimulated Raman adiabatic passage, or in short we called stirrup, which is a two-photon quantum interference phenomenon. So before I go in much detail, I just want to explain what is Feshbach association, how we make molecules from the atoms with this. So this is a method or a key technique to create molecules from ultra-cold atoms. If we like want to explain it, we can think about like you have two free atoms into a weakly bound state. Like you can have free atoms, then you somehow transform them in a weakly bound molecular state using magnetic field near Feshbach resonance. So this is a scattering property of atoms we use, and this enables control of interactions in ultra-cold gases. And this can be done when you have like the atoms have temperature of the order of a few hundreds of nanokelvin. So in that region, you can utilize the interaction property or the scattering property of the ultra-cold atoms. So you can like, if you change the magnetic field of the of the system, then the scattering property of the atoms change, and at a particular magnetic field, it like the scattering strength or scattering length of the atoms blows up, and that region is called the Feshbach resonance region. So how it works? So you consider you have two atoms in an open channel, like this is a potential diagram, potential of like atomic molecular potential, you can say. And then you have an open channel, like two atoms here in open channel that can couple to a bound state in the closed channel. It means if you have an energy E, you can bound to a state below here, like, because it has, if and that energy is less than this closed channel energy, then you basically bound in somewhere here in this potential. This is called, that's why it's called weakly bound state. And you can do that by sweeping the magnetic field across the Feshbach resonance, as I was saying. So at this somewhere here, like you just tune your magnetic field and the scattering length blows up. We know for each atoms where is the atomic like the Feshbach resonance from the theoreticians and from previous literatures. So in pictorial things, it's like that. You have two free atoms, you tune your magnetic field and you go to the bound weakly bound molecular states. So thus we prepare weakly bound Feshbach molecules, but those are not the ground state molecules. So we need to transfer those molecules into their ground state. Therefore, we use the stimulated Raman adiabatic process or passage or stirrup. So it's a three-level process. You can consider a simple three-level system. And let's say this one state is our Feshbach a molecular state, and then two state is intermediate excited state, and then three state is the ground state. So we want to transfer our molecules from 1 to 3 state, and we shine two lasers. So okay, and they have like the we shine two lasers and they have like the spontaneous decay rate, and the lasers have some detuning. Now, the basic task of stirrup is to transfer population within this system effectively and selectively from this state 1 to 3 to an initially unpopulated state via this intermediate state 2. And the complete transfer of population is achieved by using coherence of two laser fields. But we need to shine the lasers in a following way. So it's called a counterintuitive process, where your omega 2, that means the second laser, comes first before the first laser. So if I go back to this level scheme, so your second lasers comes first, then your first laser come. So that's why it's called counterintuitive process. And we have to then you need to taken care about the two photon resonance condition. So if you solve a 3-level atomic system, I'm sorry, I can't explain all this solving things here, but if you solve a 3-level system, you can see there are a particular condition which is called the two photon resonance condition, where which is delta 2 minus delta 1 should be 0, such that then your atoms or molecules transfer from this state to this state. And you need also sufficient overlap between those two pulses, which in experimental language is called transfer time. And pulse should be strong enough to maintain time evolution adiabatically. So it should be very slow. It's not that fast process. Although we do first means it's not of the order of millisecond. It should be like microsecond. So there should be no population in the intermediate state of that's why I just said you need to have a pulse sequence which is not too fast, not too slow, that your molecules get lost to some other states. Now, to understand how this works, we can just say we have a Hamiltonian after rotating wave approximation, which is basically for a 3-level system is a 3x3 Hamiltonian, which contains the Rabi frequencies omega 1 and omega 2 corresponding to both of those lasers and the detunings. Then if you solve this or diagonalize this Hamiltonian, you will get 3 eigenvalues and corresponding to that 3 eigenstates. And where this theta is basically comes from the combinations of theta and phi, or the combinations of the Rabi frequencies and the Rabi frequency and detuning. And if our interested eigenstate is A0, because you see, though this is basically a coherent superposition state of 1 and 3, and there is no contribution of 2. That means if we transfer the molecules to this state, there is no possibility that it can go back to 2 because there is no coupling or no contribution from 2 state. So, and also the population in states A plus and A minus quickly get lost from the system, and A0, as I said, is a trap state because there is no component of the excited state 2. And with this counterintuitive pulse ordering relations, we can see the mixing angle theta could be changed from 0 to pi/2, and thus we can change or transfer molecules from state 1 to state 3. And we also need to maintain this condition, the adiabatic condition, which depends on the reduced Rabi frequencies and the transfer time, or the pulsed width, and the natural line width of the excited state. So now I'm going to say how we prepare the rubidium cesium molecules in our lab. So we have rubidium atoms, cesium atoms. We cool them down to few hundreds of nanokelvin temperature simultaneously in this crossed optical dipole trap. Then we do the Fishback association, where we formed weakly bound Fishback molecules, and then we shine two lasers to do the stirrup at a particular magnetic field, because we are using this magnetic field to do the Fishback association. And then we transfer the molecules from ground state, Fishback state to the ground state, and we do a reverse stirrup to image the molecules. Before that, before going to explain how do we do imaging of the molecules, I just want to mention that we transfer the at molecules from phase-back state to the ground state with 90% efficiency, and at this magnetic field we transfer them to a absolute ground state. So here we have we transfer to a hyperfine state, which is also the ground state at that magnetic field, has the lowest energy at that magnetic field. And that after that we basically do the reverse stirrup, means the back, the mirror image of the stirrup sequence. So we transfer the ground state molecules again back to the phase-back molecules, and again we dissociate the phase-back molecules to the atoms, and then we do the absorption imaging of the remaining atoms, because we know where are those atoms after forming the phase-back association. So from that we measure, do the absorption imaging, and that numbers tells us how many molecules we have. So in general, we have 3,000 ground state molecules in the dipole trap. Okay, so that's after this. I will take a few 1 minute break. If you have any question, we can discuss now, and then I will show you what we do, very briefly, what we do in our labs with these molecules.
As speaker said, if participants have any question, then they can ask or they can write.
Okay, if there are no questions, I hope I made it clear, or I didn't make it clear at all. So I'm just moving forward.
But
Okay.
I have a question.
Oh, yeah,
Actually.
sure.
I asking if there any chance the BEC in future may any new technology advancement, which any new technology came from this BEC research.
New technology means what? What you want to expect? I mean,
I mean any new technology that help the human civilization in practical way.
human civilization in practical way. So one thing is that this kind of system is very much useful to understand your fundamental physics, your fundamental quantum physics. Then people are proposing you can use those to make the quantum computer. Although you can argue it's a very big, bulky system. Now we have to, we are in a state where we are now understanding how we make them in a quantum computer. But before that, we can understand how we can use those things to understand the fundamental parts of the quantum computer. But, people already made atoms cheap, where you can, it's a tiny bit like this, and you basically implement your atom BEC on that chip. So, and that you can use in space, like gravitometer. People are using that. So I'm not sure. And also there are something called, it's not related with the BEC, but cold atoms magnetometry, which people used to have have to in medical science, MRI and these things. So of course, I think it will give you some kind of quantum technology, new quantum advancement in far future. But before that, there are so many things you need to understand, and then you have to have very much make those complete bulk system in a small system that you can use that like portable system.
Orpita, there is a question.
Yeah, thank you.
Momita,
Mhm.
she asked what environment is required to get atoms trapped in optical lattice. Could you
Okay,
please?
so yeah, so you need first in terms of temperature, the atoms required it depends how lattice, like also how much trap depth you have for the lattice. But I think like it's always better to have a few nanokelvin temperature, like, because then like if you have BC, then you can load into the optical lattice that atoms, BC state of the atoms, because BC have like few hundred of nanokelvin or more, less than that. And that can give you an efficient loading. But even if you have like a few microkelvin, you can still load to the lattice, but then all the energy band of the lattice will, higher energy band of the lattice will be populated. So it depends what is your requirement. If you want to study some quantum simulation and something like that, then it's always preferable to have like after you load your atoms or molecules into the lattice, it populate only the lowest band of the lowest energy band of the lattice. So like
What
either you
the
sorry.
typical life? What is the typical lifetime of the optical lattice? If it is starts with the BSc, a few nanokelvin,
I think it get over more than a second.
more than a second. Okay.
Yeah, because like I will show you after in like after a few slides. We have a trap. Just I introduce that optical trap, where you can achieve the coherence time of the order of a second. Then with that trap, if you use like lattice, then you can get more than a second, basically lifetime, and as well as the coherence time. So basic thing is that just you need to prepare a system where you can get rid of that decoherence effect of the system, which is mostly coming from the trap, optical trap, due to that AC Stark shift. So for
Okay.
atoms, I think the probability like that effect is less, because the polarizability of comparing the atom and molecules is less in atoms than the molecules. So that's why in molecules we face more problem when we have molecules in optical trap.
So I have just one question. So why people think from atom to molecule? Because atoms are easy to handle. No? So why people are moving in molecules now? And
Okay, so it's kind of the way that if you have atoms, to simulate the quantum systems like this long range interactions, you need to play more trick, because you can't like easily observed in experimental system, for example the X6G model, because to get that interaction strength visibly, it's like for molecules is of the order of kilohertz, and for like atoms is even less. So it's really tough for atoms, but for molecules it's more like is kind of, if you have a proper system with molecules, then it's easier to observe those things in experimental sense.
okay, let's continue. And would be the short,
Yeah.
because I think we are out of time now.
Oh,
So
okay.
you
So I
some
will just probably 2-3 minutes.
yeah, definitely.
Next few slides. Yeah. Okay, so just to introduce, in Durham, we have 3 rubidium cesium lab. And let's start with the tweezer lab, what we do in tweezer. So tweezer lab is where we have molecules trapped in a tweezer. So one molecules in one tweezer, and recently they combine they make the tweezer with that magic light, as I just mentioned, and they found great like controlled environment and a long-lived entanglement state with the molecules between 2 tweezers, and they observe the interaction of the order of 5 Hz, which is very interesting. Then we have the microscope lab, where we basically trying to get image of the molecules directly, or like spatially resolved and spin addressing imaging. To do that, what we do, we basically have molecules in dipole trap or light sheet. Then we load those molecules in a 2D lattice where we have like we pin the molecules in lattice sites. Then due to the interspecies collision rate, we like to avoid that species collision and to get rid of those loss due to collision, we basically play a trick. We either blast rubidium and image only cesium, following the previous method I just explained, and then or we blast cesium and image rubidium in a high objective imaging lens, and this looks like this: the absorption image, the image of the site resolve um, um, image of the molecules. And now to spatially resolve the molecules, we played a trick. We send an addressing beam, which did a AC Stark shift for the molecules which have the interaction region with this beam. And for those beam, they couldn't see the microwave transition between the rotational levels, because due to AC Stark shift, their energy got split, energy states shifted. So those could see the microwave. We transfer those molecules to higher rotational states, and then we do the imaging. So we know which are at the addressing beam site. They are in n equals to 0 state, and those are in out of the addressing beam site, those are in n equals to 1 state. If you image them, they looks like this. So this like empty region is this one, and the full image looks like this. So this is a like new development from microscope lab, and it's basically very essential to reconstruct many body correlations, because we want to see address the site-to-site interactions of the molecules. Now I'm going to say in rubidium cesium mixture lab, where I am working, there how we do progressing, we have formed a magic lattice with that particular lattice light, and we load all the molecules. We have a trick to load or to prepare ground state molecules into that lattice. But before that, I just want to mention that this lattice will gives us a long rotational coherence combined with a long lifetime, and we can basically observe our interaction strength of the order of 300 of hertz, even only in like 1D vertical lattice. We have a 3D lattice. Basically, our 1D lattice is a vertical lattice and is a standing way formed by retroreflected beam, and the horizontal lattice we formed by lattice light, laser light, looks like this, like both eye cavity, both eye configuration, and we have a trick to load fishback molecules in the 1D vertical lattice, and there we could produce 3000 ground state molecules. But as our molecules temperature is not at order of nanokelvin, it's in microkelvin, so we basically populating higher ordered states of bands of the lattice. Now we need to find out a way how we can cool down the molecules so that it can only go to the load to the lowest band of the lattice. So with this, we have still a lot to do, but moving towards to the many body physics in lattices. And we recently measured the Ramsey interference spectroscopy with our magic lattice, where we basically formed this superposition of the rotational states, and we measured the contrast of the Ramsey fringe as a function of laser detuning to like lattice laser detuning to know where we got maximum contrast. Maximum contrast means less decoherence or minimum decoherence. So we want to operate our laser at that frequency to maintain the magic condition. Apart from this, we are also parallelly working on the direct imaging of molecules. As I mentioned that we do now the imaging like all the stirrup, like reverse process, which is very destructive because you lose all the molecules from your system and you, at the end of the day, you only have the atoms left. Although those basically saying you about the molecules, but still. So imaging is a key for state detection methods in quantum control and information processing application. So the closed cycling transitions between the ground and excited state solve the problem for neutral atoms and ions, but for molecules or bialkali molecules, we don't have closed or quasi-closed cycling transitions. So this makes it difficult to image directly. So there is a proposal, a theory proposal, and for so where people propose that you can use a polarization rotation technique to detect the rotation of the light, and from that you can infer the number of atoms of the or number of molecules, because that angle of rotation depends on the number of molecules. So I'm not going to explain in details, but if you are interested, then we can discuss in question answer round. So this is a simulated image. Like original proposal is to just detect the transmission from this PBS, but we can have the reflections also, and we can put that in the camera, and then we can detect the contrast of the transmission and reflection, which is like this. And this simulation is done considering all the practical parameters of our existing camera we have. And we found the transition where we want to, like which light we want to use for imaging directly the molecules. And we currently doing the spectroscopy of molecular spectroscopy to find that transition more precisely. And I can say that we found the transition. So the next way is to measure the other parameters of these transitions before we move to the imaging setup. So with this, I want to introduce our group in Durham. So Simon Cornish is our PI. Phil Gregory is University Research Fellow. He's also our, I'm working with him, and he was the previous postdoc in our group, in our lab. And Albert is our current PhD student, and we have some intern student also. And I also want to thank all the theoretical collaborators, because without them, it's really difficult to understand what's going on. And at the end, I want to thank you all. And I'm open for any questions.
So, what I can say after this mind-blowing lecture, because you covered a lot of interesting experimental setup and nothing. So okay, I feel really proud that I worked with Orpita during his PhD time. Actually, we worked
It's
together.
my pleasure, sir.
So, okay. So, from MSc time, actually. So,
Yeah.
okay. So, if there are few questions, so we can take out. And Orpita, a lot of students are asking for PPT. So, I told them that they can directly communicate with you via email. And it is,
Yeah, sure.
up to
Yeah.
you. So, if there is any question, so you can ask, and Orpita clarify your query. Okay.
Hi.
Yeah, Momita.
Yeah.
Yeah.
Presentation, actually lots of experimental details was there. So I have a query about like simulation purpose. Like you can say in dipolar BC, there is long range dipole-dipole interaction is there. So can we consider also like short range contact interaction together with long range dipole-dipole interaction? Like can we combine two types of potential together for our simulation purpose and all?
Like for I mean, to do simulation for what? Like for what understanding?
Like
Just
for
to
calculating
see.
energy on any collective from excitations or dynamic study.
I think like molecular potential already considered all the contact interactions,
Okay.
and like the molecular potential I just show you here, this one. And then if you like, when we want to do like only simulate the quantum magnetism things, I think there just only the long range interactions is essential. I'm not
Okay.
sure like,
The
or I
long range
don't
will
know
be
in
prominent.
details.
We cannot take into account two types of potential together.
So
I'm
I
also
don't think,
confused. Like,
yeah. Uh-huh. I mean, I think there the more like dominant interaction is the dipole-dipole long-range interaction.
yeah.
So I'm not also sure how effective short-range interactions
Basically,
is
I was
there.
interested like to study the competition between long range and short range type potential. That's why actually I want to incorporate two types of.
Okay. Yeah. Yeah, I'm not like that much expert in the simulation though, but you can check like
I
some
can explore like that. Yeah.
yeah, previous like some previous studies in molecular
Yeah.
fields, like the theoretical stuff.
Okay, I'll check that.
Okay. Yeah, I
Thank
also
you.
enjoyed your talk a lot. Your talk basically helps me to skip other stuff, like
Thanks.
to explaining the basic
Yeah,
physics things. Yeah.
okay, we can contact later. Bye.
Okay.
Okay, I think there is no more question. So if there is no more question, then we can thanks Orpita again for spending her valuable time and for such a excellent.
It's always my pleasure, sir, to, and also it's very interesting to give presentation in front of undergraduate and master student, because like I don't know how they think now, like in the bigger picture sense. And yeah, but I'm not sure like how easily I explain the experimental techniques, but it's really complicated to explain also.
Yes, in India, you know that our scenario there, we are always lacking in the experiment. So it is very difficult for the student to understand what is PBS,
Yeah.
lens, or it is lens mount and other stuff, AOM, UM, everything. It's very
Yeah.
so for them, CCD means normal CCD, but the CCD you used in your experiment, which is
Yeah.
completely different and highly sophisticated.
Highly
So,
sophisticated, yes.
okay. So I think now the closing remarks given by the Shubhayu. So Shubhayu, can you start? So
Yeah, I'm beginning the good afternoon.
Okay.
Good afternoon, everyone. I, Shubhayu Chaudhary, Assistant Professor of Physics, now bring this webinar to a close with the vote of thanks. We are extremely grateful to both the speakers, Dr. Momita Indra of IIT Guwahati and Dr. Orpita Das of Durham University, UK, for their insightful and informative talk. We are truly honored to have distinguished guests, teachers, faculty members, researchers of various laboratories, and staff of different institutions whose online participation has made this webinar successful. We are deeply indebted to the President of our college, Dr. Bojokishore Goswami, Honorable Member of Legislative Assembly, for patronizing the event. We offer our heartfelt thanks to the teacher in charge and the Secretary of Governing Body and Chairman of this webinar, Dr. Subroto Rai, for granting permission to organize this event. We thank all the members of the organizing committee, advisory committee, IQAC members, teachers, students of Department of Physics, as well as all the staff of Santipur College for their cooperation. We express our gratitude and special thanks to Dr. Dipankar Bhattacharya,
Coordinator of IQAC, Dr. Amrita Chakraborty, Assistant Professor of English, Santipur College, and our ex-student Shumon Kumar Pal, now pursuing integrated PhD in IISc Bangalore, who worked with passion and commitment to give concrete shape to the entire event. So thank you. We regret any technical issue or inconvenience. Thank you again, and warm wishes to all. So the webinar ends here. Thank you again. Okay, Dipankar.
Okay, then we finish.
Okay.
So, okay. So I want to make one comment. So if any student or any participant face any problem regarding certificate, please feel free to write us. We'll definitely solve the problem. Otherwise, you just fill up the Google link and you will get it. Okay. So again, thanks Momita and Orpita for their excellent job. Really, this is a great moment as a teacher. So when we see that our students are in such a position, they can teach us. And also Shumon is always attached to the Department of Physics, and Shumon, Rishit and others, Rameshwar, Rana, they always encourage us. So okay, okay. So I think I should stop now. Okay, thanks to everybody.